Let us start with our topic of organic chemistry, that is nitro compounds. Nitro compounds constitute an important class of organic compounds. These may be considered to have been derived from the corresponding hydrocarbons by the replacement of one or more hydrogen atoms by the nitro group. They are further classified as aliphatic or aromatic nitro compounds according as the nitro group is attached to alkyl or an aryl group. RNO2 is an aliphatic nitro compound where R is an alkyl group. ARNO2 is aromatic nitro compound where AR is an aryl group. Nitroalkanes are further classified as primary, secondary and tertiary according as the nitro group is attached to a primary, secondary or a tertiary carbon atom. This is the primary nitroalkane as you can see from this figure, and there are secondary and tertiary nitroalkanes. Since nitro group is isomeric with the nitrite group, nitro compounds are isomeric with alkyl or aryl nitrides. The chemical properties of these two isomeric classes of organic compounds are quite different, but the nitro compounds are much more stable and find number of applications both in the laboratory as well as in the industry. Therefore, in this unit we shall briefly study the chemistry of nitro compounds only. Structure of nitro group. According to valence theory, the structure of nitroalkanes may be written as Rn double bond O or Rn positive double bond O, O negative. First is the classical structure and the second is the polar structure. Polar structure of nitroalkanes is supported by their large dipole moments. Thus, nitroalkanes may be represented as a resonance hybrid of following two canonical structures. The resonance hybrid structure third suggests that the two NO bonds are equal. The spectroscopic and diffraction studies have shown that bond length of NO bonds is 121 picometer in nitromethane, which lies in between NO single bond length of 136 picometer and N double bond O bond length of 114 picometer. Nomenclature. Nitro compounds are solely named by the IUPAC system. The name of any nitro compound is derived by adding the prefix nitro to the name of corresponding alkane or arene. Accordingly, aliphatic nitro compounds are called nitroalkanes, while aromatic nitro compounds are called nitroarenes. Positions of nitro group and other substituents, if any, on the parent nitroalkane or the nitroarene are indicated by Arabic numerals 1, 2, 3, etc., with the carbon atom bearing the nitro group getting the lowest possible number. For aromatic nitro compounds, prefixes O for 1, 2, meta for 1, 3, and para for 1, 4 are also used. Some typical examples are given below. CH3NO2 nitromethane, CH3CH2NO2 nitroethane, CH3CH2CH2NO2 is 1 nitropropane, CH3CHNO2CH3 is 2 nitropropane. Accordingly, there are other classes of nitro compounds such as nitrobenzene, O-nitrotoluene, P-nitrotoluene, M-dinitrobenzene. Then there is a preparation of nitro compounds. Nitroalkanes are usually prepared by the following methods. From alkanes, alkanes undergo nitration only with fuming HNO3 in the vapor phase at 673 Kelvin to form nitroalkanes. This method is called vapor phase nitration. Methane plus fuming HNO3 at 673 Kelvin gives CH3NO2, that is nitromethane, but in low yield, plus water. Limitation of this reaction. Nitration of higher alkanes not only gives a mixture of all the isomeric nitroalkanes, but other nitroalkanes containing lesser number of carbon atoms, resulting through cleavage of carbon-carbon bonds are also formed. Besides these, oxidation products like CO2, NO2, H2O are also formed. Ethane, when treated with fuming HNO3, gives nitroethane and nitromethane. Propane, when treated with fuming HNO3, gives 1 nitropropane and 2 nitropropane in 25% and 40% yield, and 1 nitroethane in 10% yield, nitromethane in 20% yield. The reaction occurs by a free radical mechanism, and the ease of substitution of hydrogen follows the order tertiary, secondary, and primary. Due to the formation of complex mixture of products, this method is not suitable for lab preparation of nitroalkanes. However, this method is widely used for the commercial preparation of nitroalkanes since they are used as industrial solvents only. Second is from alkyl halides. Alkyl bromides and iodides, especially primary and secondary reacts with silver nitrate in alcohol to give excellent yields of nitroalkanes, along with small amounts, that is 10 to 15% of alkyl nitrites. Alkyl halide plus silver nitrite gives nitroalkane major plus alkyl nitrite minor in the presence of alcohol. 1 bromobutane similarly gives 1 nitrobutane and N-butyl nitrite. Explanation: this reaction is an example of nucleophilic substitution reaction. Nitrite ion, like cyanide ion, is an ambident nucleophile since it has two sites, oxygen and nitrogen, through which it can attack on alkyl halide. Whereas attack through nitrogen gives nitro compounds, attack through oxygen gives nitrites. Likewise, silver nitrite with alkyl halide iodide gives nitroalkane, and sodium nitrite with alkyl halide gives alkyl nitrite. Alkali metal nitrites are ionic compounds and hence have a negative charge on one of the oxygen atoms. Nucleophilic attack through this negatively charged oxygen atom on the alkyl halides mainly gives alkyl nitrites. In contrast, silver nitrite is a covalent compound and hence doesn't have a negative charge on oxygen atom. Instead, both oxygen and nitrogen atoms carry lone pair of electrons since nitrogen is less electronegative than oxygen. Therefore, lone pair of electrons on nitrogen are more easily available for bond formation. In other words, nucleophilic attack through a nitrogen and hence silver nitrite predominantly gives nitro compounds. What are the demerits? Aromatic nitro compounds cannot be prepared by this method. This method is not suitable for the large-scale preparation of nitro compounds. Third, from tertiary alkyl amines. Primary amines containing a tertiary alkyl group on oxidation with KMnO4 gives excellent yields of corresponding nitroalkanes. Likewise, when tertiary butyl amine reacts with KMnO4, it gives 2-methyl-2-nitropropane in 83% yield. Preparation of nitroarenes. Nitroarenes are invariably prepared by direct nitration of arenes with a mixture of concentrated HNO3 or fuming HNO3 and concentrated sulfuric acid. For example, when benzene reacts with concentrated HNO3 in the presence of concentrated H2SO4 at 333 Kelvin gives nitrobenzene plus water. The mixture of concentrated HNO3 plus concentrated sulfuric acid used for nitration of aromatic compounds is called nitrating mixture or the nitrating agent. Other nitrating agents which have been used for the nitration of aromatic compounds are nitric acid, acetic anhydride mixture, acetyl nitrate, nitronium perchlorate, nitronium tetrafluoroborate, and N2O5, etc. Mechanism: nitration is a typical example of an aromatic electrophilic substitution reaction in which nitronium ion acts as an electrophile. Function of sulfuric acid is not that of a dehydrating agent, but acts on HNO3 to form the reactive nitronium ions, as shown below. The electrophilic substitution reaction occurs by following two-step mechanism. Benzene and other arenes are electron-rich molecules. In the first step, the electron-rich benzene molecule nucleophile attacks nitronium ion electrophile, leading to the formation of a carbocation which is stabilized by resonance. Accordingly, benzene attacks on nitronium ion, and then it is this step is slow, and then it is followed by resonance stabilized carbocation and finally resonance hybrid. During this step, the aromatic character, that is resonance energy of 150 kJ, is sacrificed. As a result, this step is slow and hence is the rate determining step of the reaction. Step 2. In the second step, the carbocation 1 formed in step 1 loses a proton to yield nitrobenzene. Since during this step, the aromatic character of benzene ring is restored, therefore this step is fast and hence doesn't affect the rate of the reaction. Evidence in support of the mechanism. This mechanism is supported by isotope effect. It has been found that when hexadeuterobenzene is nitrated, the rate of nitration is exactly the same as that of benzene. Since a carbon-deuterium bond breaks more slowly than carbon-hydrogen bond, therefore the loss of proton is not the rate determining step. Had it been so, the rates of nitration of benzene and hexadeuterobenzene would have been different. Benzene plus HNO3 give NH2SO4, that is nitration gives nitrobenzene, and hexadeuterobenzene in the presence of HNO3 and H2SO4 gives 2,3,4,5,6 pentadeuteronitrobenzene. Choice of nitrating agent. Choice of nitrating agent to be used for the nitration of a given compound depends upon the following two factors, that is, nature of compound to be nitrated, number of nitro compounds to be introduced, and the presence of electron donating substituent like methyl, methoxy, OH, NH2, etc. activate the benzene ring by stabilizing the intermediate carbocation. Therefore, nitration of these compounds is carried under mild conditions. For example, nitration of phenol occurs with a dilute HNO3 even at room temperature. Phenol, when react with dilute HNO3, gives O-nitrophenol and para-nitrophenol. In contrast, presence of electron withdrawing groups such as NO2, COOH, CnSO3H, that is halogens, deactivate the ring by stabilizing the carbocation, destabilizing the carbocation. Therefore, for nitrating such compounds, or when it is required to introduce more than one nitro group, the nitration is carried out not only by using a strong nitrating mixture, but a higher temperature is also required. For example, nitration of nitrobenzene, which contains electron withdrawing NO2 group, is carried out with a mixture of concentrated HNO3 plus concentrated sulfuric acid. Nitrobenzene, when react at 393 Kelvin, gives M-dinitrobenzene. Physical properties of nitro compounds. Physical state, order, color. Nitroalkanes are colorless when pure, pleasant smelling liquids. Aromatic nitro compounds can be either pale yellow liquids or solids with distinct smells. For example, nitrobenzene is a pale yellow liquid having the smell of bitter almonds and is known as the oil of myrrh. Boiling points. Both nitroalkanes and nitroarenes are highly polar compounds, dipole moment between 3 to 4D, and thus have strong dipole moments. As a result, they have much higher boiling points than hydrocarbons of comparable molecular masses. Further, nitroalkanes also have much higher boiling point than the less polar isomeric alkyl nitrides. For example, boiling point of ethyl nitride is 261 Kelvin, while isomeric nitroethane has a boiling point of 388 Kelvin. All the nitroalkanes and nitroarenes are heavier than water. Nitroalkanes are sparingly soluble in water, while nitroarenes are insoluble. However, both nitroalkanes and nitroarenes are readily soluble in organic solvents. When heated strongly, polynitro compounds decompose with explosive violence. Some important chemical reactions of nitroalkanes are described below, that is tautomerism. Like aldehydes and ketones, nitroalkanes containing alpha hydrogen atoms, that is primary and secondary nitroalkanes, show tautomerism. For example, nitromethane exists in two tautomeric forms, that is 1 and 2 nitromethane, and the second is acynitro form or isonitro form or nitronic acid form. Nitroform 1 is called the pseudo-acid form, while the isonitroform second is called the acenitroform or nitronic acid. The equilibrium, however, almost completely lies towards left due to resonance within the nitro groups, stabilization of nitroform 1. Similarly, nitroethane and nitropropane, 2-nitropropane, shows tautomerism, while aromatic nitro compounds, that is nitrobenzene, M-dinitrobenzene, etc., which do not contain alpha hydrogen atom, do not show tautomerism. Second is the acidic character. The alpha hydrogen atoms of primary and secondary nitroalkanes are weakly acidic and thus can be abstracted by strong bases such as aqueous NaOH. Therefore, primary and secondary nitroalkanes dissolves in aqueous NaOH to form salts. For example, nitroalkane, when react with sodium hydroxide, gives the salt. The main reasons for the acidic nature of primary and secondary nitroalkanes are the strong electron withdrawing inductive effect of nitro group and the resonance stabilization of carbanion formed after removal of proton. Although primary and secondary nitroalkanes are weakly acidic, yet as compared to aldehydes and ketones, they are twice as strong. For example, pKa of nitromethane is 10.2, while that of acetone is 20. Nevertheless, nitroalkanes are neutral to litmus. Acidification of sodium salt 1 with a weak acid gives the nitro analog of an enol called the acenitrotomer. Unlike the enols of aldehydes and ketones, which are readily converted into keto form, the conversion of acenitroform form into the nitro form is a relatively slow process. Consequently, acenitroform form can be regenerated as a metastable intermediate in high concentration by careful acidification of salts. The acenitroform derivatives are relatively stronger acids, as is evident from their pKa values. Reactions of acenitroform with electrophiles and nucleophiles is one of the remarkable features of AC nitroform is that they can behave as nucleophiles as well as electrophiles and thus react with electrophilic and nucleophilic reagents. Reactions in which AC nitro derivatives acts as nucleophiles. Some reactions of this type are discussed below. Aldol condensation. The carbon ion of nitroalkanes being nucleophilic reacts with electrophilic agents such as aldehydes and ketones to form aldol type addition products which spontaneously undergo dehydration to give alpha beta unsaturated nitro compound. For example, nitromethane when react with base gives this anion. Acetaldehyde with a nucleophile reacts with water to give 1 nitropropene. Driving force for this reaction is the main gain in stability due to conjugation of ethylenic double bonds with a double bond of nitro group. Second is Michael addition. Like aldehydes and ketones, alpha beta unsaturated carbonyl compounds acts as electrophiles and thus react with nucleophilic AC nitroform to form Michael type addition products. For example, nitroalkane when react with a base gives AC nitroform with Michael addition with this electrophile gives addition product. Third is halogenation. AC nitroforms generated from primary and secondary nitroalkanes in the presence of alkali being nucleophilic react with electrophiles such as halogens, chlorine or bromine in the presence of alkali to form halonitroarenes. During this reaction, all the alpha hydrogen atoms of nitroalkanes are successively replaced by halogen atoms. For example, nitromethane when plus chlorine plus NaOH gives chloropicrin. Then nitroethane with chlorine in the presence of NaOH gives 1 chloro 1 nitroethane. Then finally 1 dichloro 1 nitroethane. Tertiary nitroalkanes do not undergo halogenation because they do not have alpha hydrogen atoms. Chloropicrin obtained above is used as an insecticide as well as a constituent of tear gas. Reactions in which acetnitroforms acts as electrophiles. An important reaction of this type is Neff carbonyl synthesis. When the solution of sodium salt of nitronic acid is acidified with H2SO4 at room temperature, primary nitroalkanes gives aldehyde while secondary nitroalkane gives ketones. During these reactions, the acetnitroform acts as the electrophile and water as the nucleophile. For example, sodium salt of nitronic acid gives 50% sulfuric acid and it gives electrophile when nucleophile water reacts with this to give aldehyde. Similarly, sodium salts of nitronic acids derived from secondary nitroalkanes or treatment with 50% sulfuric acid give ketones. This reaction is called Neff carbonyl synthesis. The main disadvantage of Neff carbonyl synthesis is that the reaction is often violent and gives unsatisfactory results. Hydrolysis. Primary nitroalkanes when treated with boiling HCl or 85% sulfuric acid undergo hydrolysis to form a carboxylic acid and the corresponding salt of hydroxylamine. That is nitroalkane when react with HCl and water gives carboxylic acid plus hydroxylamine hydrochloride. This reaction is used for the manufacture of hydroxylamine. In contrast, secondary nitroalkanes upon hydrolysis with boiling HCl gives a ketone and nitrous oxide. That is secondary nitroalkane in boiling HCl gives ketone plus nitrous oxide. Two nitropropane in boiling HCl gives acetone plus nitrous oxide. Tertiary nitroalkanes, however, do not generally undergo hydrolysis with hydrochloric acid. Fourth is action of nitrous acid. Primary, secondary, and tertiary nitroalkanes behave differently towards nitrous acid. Primary nitroalkanes react with nitrous acid to form nitrolic acids, which dissolve in alkalis to form a red solution. Secondary nitroalkane reacts with nitrous acid to form blue-colored pseudonitrol, which do not dissolve in alkali. That is when secondary nitroalkane reacts with HNO, that is HNO2, nitrous acid, pseudonitrol forms. Tertiary nitroalkanes do not react with nitrous acid, and since they do not have alpha hydrogen atom. Fifth is the Manish reaction. Primary and secondary nitroalkanes also undergo Manish reaction. For example, when primary nitroalkane reacts with methanol and dimethylamine in the presence of acid. This following compound forms. That is when secondary nitroalkane react with methanol diethyl in the presence of diethylamine in the acidic medium, it gives this following compound. This reaction can be used for the preparation of nitroamines and diamines, etc. Reduction. One of the most important reactions of nitro compounds is the reduction. Depending upon the nature of the reducing agent and pH of reaction medium, nitroalkanes give different products as shown below. That is reduction in acidic medium. Nitroalkanes can be reduced to the corresponding primary amines by a combination of some active metals like zinc, iron, or tin and concentrated hydrochloric acid. For example, nitroethane when reacted with tin in the presence of HCl gives ethylamine and salts. Reduction in neutral medium. In the neutral medium, zinc dust and ammonium chloride solution, nitroalkanes are reduced to corresponding hydroxylamines. For example, nitromethane in the presence of zinc NH4HCl gives N-methyl hydroxylamine. Third is catalytic reduction or reduction with lithium aluminum hydride. Nitroalkanes can also be reduced to the corresponding primary amines with either lithium aluminum hydride or with hydrogen in the presence of a catalyst such as Re nickel, platinum, palladium, carbon, and ethanol. Some important reactions of nitroarenes are discussed below. Acidic nature. Unlike primary and secondary nitroalkanes, nitroarenes do not have any alpha hydrogens. Therefore, like tertiary nitroalkanes, they do not exhibit acidic character or tautomerism. However, nitro compounds having two or more nitro groups attached to the benzene ring are somewhat acidic. Thus, polynitro compounds often react with cold aqueous alkali to form strongly colored salts. The strong minus I effect of 3NO2 groups stabilize carbonyl. Second is reduction. One of the most important reactions of nitro compound is their reduction to primary amines. This reduction is believed to occur through the following stages. First nitro compound, then nitroso and substituted hydroxylamine, and finally a primary amine. Final product, however, depends upon the pH of reaction medium and nature of reducing agent. First, reduction in acidic medium. Like aliphatic nitro compounds, aromatic nitro compounds can be reduced to the corresponding amines by a combination of some active metals like zinc, iron, or tin and concentrated hydrochloric acid. Nitrobenzene in the presence of FeHCl gives first aniline hydrochloride. When treated with NaOH gives aniline. Under acidic conditions, the intermediate products nitroso compounds and hydroxylamines are reduced even more readily than the parent nitro compound, and hence only the primary amine is obtained as the final product. Mechanism. The mechanism of reduction of nitro compounds to amines involves a number of steps in which addition of electrons and protons from the acid takes place, and nitrosobenzene and phenyl hydroxylamine are the intermediates. You can see these steps. And finally, anilinium ion forms. Catalytic reduction. Like aliphatic nitro compounds, aromatic nitro compounds can be reduced to the corresponding primary amines with hydrogen in the presence of a catalyst such as Re nickel, platinum, or palladium carbon in ethanol. When nitrobenzene reacts with palladium carbon in the presence of ethanol and hydrogen, it gives aniline plus water. Reduction in the neutral medium. In the neutral medium, zinc dust and ammonium chloride solution, aromatic nitro compounds like aliphatic nitro compounds are reduced to the corresponding hydroxylamine. These hydroxylamines, when warmed with Tollens reagent, are easily oxidized back to the corresponding nitroso compounds and thus reduce Tollens reagent to metallic silver. This reaction is used as a test for nitro compounds under the name Baker-Mulliken's tests. Reduction in alkaline medium. The reduction of aromatic nitro compounds in the alkaline medium gives different, that is bimolecular reduction, products depending upon the nature of reducing agent employed. Nitrobenzene, when react with sodium arsenite NaOH or glucose in the presence of NaOH, gives azoxybenzene. When nitrobenzene reacts with zinc NaOH in the presence of methanol, it gives azobenzene, and when nitrobenzene reacts with zinc in the presence of NaOH, it gives hydrazobenzene. These bimolecular reduction products are actually formed by the condensation of primary products of reduction, that is nitrosobenzene and phenyl hydroxylamine. Azoxybenzene is formed by the base-induced condensation of nitrosobenzene and phenyl hydroxylamine. When N-phenyl hydroxylamine reacts with nitrosobenzene, it first forms an intermediate which finally loses the water molecule and base molecule to form azoxybenzene. Similarly, it can be shown that further reduction of azoxybenzene first gives azobenzene and then hydrazobenzene. Reduction with lithium aluminum hydride. Reduction of nitrobenzene with lithium aluminum hydride also yields azobenzene. It may be noted here that reduction of aliphatic nitro compound with lithium aluminum hydride, however, gives the corresponding primary amines. Electrophilic reduction. Electrolytic reduction or of nitrobenzene in weakly acidic medium gives aniline, but in strongly acidic medium it gives para-aminophenol, obviously through the acid catalyzed rearrangement of initially formed phenyl hydroxylamine. Nitrobenzene in the presence of weakly acidic medium gives aniline. Nitrobenzene in the presence of strongly acidic medium gives N-phenyl hydroxylamine, which undergoes rearrangement to form para-aminophenol. Another reaction is selective reduction. If two or more nitro groups are present in the benzene ring, it is possible to reduce one of them without affecting others. Such reductions are called selective reductions. For example, reduction of M-dinitrobenzene with sodium or ammonium sulfide gives M-nitroaniline. This reduction of nitro compounds with sulfides and polysulfides is called xenin reduction. Third is electrophilic substitution reactions. Nitro compounds, like other aromatic compounds, undergo electrophilic substitution reactions such as halogenation, nitration, and sulfonation. Since nitro groups is a powerful electron withdrawing group, it is strongly deactivating and meta-directing. This may be explained as follows. Nitrobenzene can be represented as a resonance hybrid of following structures. It is evident that nitro group, because of its electron withdrawing nature, reduces electron density more at ortho and para than at meta. In other words, electron density is comparatively more at meta positions than at ortho and para positions. Therefore, nitro group is meta-directing. Further, since the NO2 group is strongly deactivating, therefore these reactions occur only under drastic conditions. Nitrobenzene, when reacted with fuming HNO3 plus concentrated sulfuric acid, gives M-dinitrobenzene. When nitrobenzene reacts with bromine in the presence of iron, it gives M-dinitrobenzene. When this reacts with fuming H2SO4, it gives M-nitrobenzene sulfonic acid. It may be noted here that because of strong electron withdrawing nature of nitro groups, the electron density on the benzene ring decreases to such an extent that M-dinitrobenzene doesn't undergo further nitration to give same trinitrobenzene. Therefore, it is prepared by indirect route. Nitrobenzene doesn't undergo Friedel-Crafts reaction. It is because of this reason that in many Friedel-Crafts reactions, nitrobenzene is used as a solvent. Another advantage of using nitrobenzene as a solvent in FC reactions is that because of its highly polar nature, it dissolves in anhydrous AlCl3. Fourth is nucleophilic substitution reactions. The presence of the positive charge at ortho and para positions in resonance structures, second say fourth, suggests that nitrobenzene can also undergo nucleophilic substitution reactions at these positions. These reactions, however, occur with strong nucleophiles under drastic conditions. For example, nitrobenzene, when fused with solid KOH, gives a low yield of mixture of ortho and para nitrophenols. Nitrobenzene, when react with solid KOH, fused to form O-nitrophenol and para-nitrophenol. The mechanism of this reaction is an example of bimolecular substitution reaction. In the first step, the nucleophilic adds to the benzene ring to form a carbanion, which is stabilized by resonance, also involving the nitro group. In the second step, the carbanion 1 loses a hydride ion, which is a very strong base and hence a poor leaving group. Therefore, the reaction is usually carried out either at the higher temperature or in the presence of an oxidizing agent which oxidizes hydride ion to hydrogen. Complete mechanism is outlined below by considering the formation of para-nitrophenol. When nitrobenzene reacts with base, it gives, in the presence of nucleophilic attack, it first gives resonance stabilized carbanion, which again gives resonance hybrid. In the step 2, this hydride ion is lost and the molecule para-nitrophenol is formed. Again, there is a reaction that is called replacement of nitro group. We have seen that nitro group of nitrobenzene remains intact on treatment with alkali. However, this nitro group can be replaced as nitrite ion by nucleophiles if another group is present at ortho or para positions. For example, when O-dinitrobenzene reacts with aqueous KOH, it gives O-nitrophenol and KNO2. Similarly, when it reacts with ethanolic potassium hydroxide, it gives O-nitrophenitol plus KNO2. When react with ammonia, it gives O-nitroaniline plus N2 plus water. Finally, we have to study picric acid. Direct nitration of phenol with mixture of concentrated HNO3 plus concentrated sulfuric acid gives only a low yield of picric acid, because picric acid, being a strong oxidizing agent, oxidizes phenol to terry products. It is therefore prepared commercially by the following methods. From phenol, phenol is first sulfonated to give phenol 2,4-disulfonic acid, which is then nitrated. During nitration, the two sulfonic acid groups are replaced by nitro groups, and a third nitro group is introduced at the ortho position. Second, from chlorobenzene, picric acid is obtained from chlorobenzene by the following sequence of reactions. Chlorobenzene, when react with HNO3 in the presence of H2SO4, then 2,4-dinitrochlorobenzene, and when react with aqueous Na2CO3, that is nucleophilic substitution, it gives 2,4-dinitrophenol. When in the presence of HNO3 and H2SO4, that is nitration, it gives picric acid. Physical properties: it is a yellow crystalline solid that is melting point 395 Kelvin, sparingly soluble in water but readily soluble in alcohol and ether. It has a bitter taste and hence the name picrose bitter. Chemical properties: some important chemical properties of picric acid are described below. First is acidic nature. Due to the presence of three nitro groups, picric acid is a very strong acid, that is pK 0.71, hence decomposes carbonates and bicarbonates, evolving CO2 gas. Reaction with PCl5: when treated with PCl5, it forms picryl chloride. The chlorine atom in picryl chloride is very reactive and thus get hydrolyzed to phenol on just boiling with water. On treatment with concentrated ammonia, picryl chloride gives picramide. Third is reduction. On selective reduction with Na2S, picric acid gives picramic acid. Picric acid gives picramic acid. Formation of picrates: it forms charge transfer complexes known as picrates with electron-rich compounds such as aromatic hydrocarbons, mesitylene, naphthalene, anthracene, amines, and phenols. Picric acid, when react with mesitylene, forms a charge transfer complex known as picrate in the presence of alcohol. Picrates are yellow, orange, or red colored solid with definite melting points and hence are often used as derivatives to characterize above classes of compounds. Picric acid is used as an explosive, as a direct yellow dye for wool and silk, and in medicine as an antiseptic for burns. It is also used as a lab reagent for characterization of purification and polynuclear hydrocarbons, aromatic hydrocarbons, amines, and phenols. Halonitroarenes. Arenes containing both halogen and nitro group are called halonitroarenes. For example, there are three isomeric halonitroarenes having one halogen atom and one nitro group attached to the benzene ring. Chemical reactivity of halonitroarenes. Haloarenes are unreactive towards nucleophilic substitution reactions, but the presence of nitro group at ortho and para positions with respect to halogen facilitates nucleophilic substitution reactions of halonitroarenes by stabilizing the intermediate carbanion as shown below. In step 1, this para-nitrochlorobenzene reacts slowly with hydroxyl ion to form this carbanion. In step 2, this carbanion loses a molecule of chloride ion. It is a fast reaction to form 4-nitrophenol. Evidently, more the number of nitro groups at ortho and para positions, that is, with respect to the halogen, more reactive is the halonitroarene. That is 4-nitrochlorobenzene when react with 5% NaOH at 433 Kelvin in the dilute HCl, it gives 4-nitrophenol. When 2,4-dinitrochlorobenzene, it gives aqueous in the presence of aqueous Na2CO3 in 413 Kelvin, it forms 2,4-dinitrophenol with hydrolyzing with dilute HCl. 2,4,6-trinitrochlorobenzene, that is picryl chloride, in the presence of water at 323 Kelvin gives picric acid. It may, however, be noted that presence of nitro groups at meta position with respect to the halogen doesn't activate the halogen to the same extent as ortho and para positions, since the carbon ion is only stabilized by the weak minus I effect and not by the strong minus R effect of the nitro group. So this was all about our chapter. Thank you so much.